I have the honor to present the last paper. Our speaker, unfortunately, was unable to make it here. Dr. Rashid is an associate professor in the Department of Civil Engineering at Syracuse University, and he obtained his PhD from the University of Adelaide in Australia in 2008. And so I will do my best to present this paper. Probably some of the detailed questions will be needed to direct it towards him. But the title of the presentation is Flexural Strength and Behavior of Inverted T Precast Concrete Beams Reinforced with Modified Smooth CFRP Bars. And so essentially in this work, CFRP smooth bars are used, and some efforts are undertaken to try to improve the bond performance of those bars through special treatments. Introduction. So I think a lot of this is well known for us in terms of steel reinforcement, corrosion, and of course some of the distress that occurs as it's related to deterioration of bridges and structures that are subjected to external environments. This application of CFRP bars as a flexural reinforcement and reinforced concrete structures is to try to overcome the corrosion-related issues. And here you can see some samples of FRP bars on the left and a cross-section configuration of a test beam. There's various types of FRP products and various types of FRP surface treatments. At the top, of course, we can see a plain or smooth bar, ribbed, indented, braided, and usually sand-coated with some type of epoxy or resin system. And I believe even in Australia they have some laser-etched bars that are intended to get, in addition to friction, some bearing capacity. But that laser etching, I know, reduces the cross-sectional area at locations along the bars. So it's sort of, you're sacrificing some of the cross-sectional area to maybe improve some of the bond performance. But essentially in this study, what the research team was looking at is taking smooth bars that again are going to have reduced bond performance compared to some of these other bars you see below with different surface treatments. And the objective was to really improve the bond strength of smooth CFRP bars with a new technique and to apply the modified smooth bars as a flexural reinforcement in precast beams. And so this work looks at a T-beam section. And again, the specific objectives was to obtain bond behavior of this modified smooth bar, number one, and number two, to evaluate the flexural responses of the inverted T-beam with this modified coating treatment. The paper presents a pretty thorough overview of research paper literature survey. This highlights some of the key points. I won't read through all of them, but again, you have the chemical adhesion, friction, and in some cases you may get some mechanical interlocking that occurs. For smooth bars, you're going to miss some of that mechanical or bearing interlocking, of course. So in this study, a new anchorage system is looked at with the modified surface treatment. And so if you look at the factors that affect bond strength of CFRP bars in concrete, the boxes are well-known characteristics that affect bond, whether it's a top bar, effects due to, depending on how the concrete is consolidated, deformed, non-deformed, etc. The red box with the dashed line is what the research team was focused on. generating additional knowledge on. So epoxy-coated additional anchorage system for smooth bars. This is a summary of the findings on the right from the literature review. I'll just sort of pause for a moment. You can look at some of these. Some of the top work looked at continuous concrete beams reinforced with CFRP bars. The second study looked at beams reinforced by steel FRP composite bars, so kind of a hybrid investigation. Third one looked at bond slip. And you can see that some of these looked at smooth bars, spiral wrap bar, BFRP in the case of the bottom one, and some of the key findings that are highlighted in bold. And moving on to some of the additional papers that were investigated, higher FRP reinforcement ratio. There's a lower rate in increasing ultimate moment capacity that we know about, and different types of failure modes may occur under flexural testing, of course, whether it's compression controlled or tension controlled. So in terms of the factors affecting the behavior with CFRP, what this study looked at was under reinforced limit state condition for these additional anchorage applied to the CFRP bars. So this is a summary takeaway points from the literature review. Porous bond is, of course, with smooth CFRP bars. Some of the short embedment pullout testing I presented yesterday morning, that was clearly the case for smooth CFRP bars as well, and short embedment lengths. And some of the recommendations, smooth CFRP bars are not recommended to be applied in structural applications from some of these papers, and new techniques to enhance the bond strength was reported in some of the papers. In this study, precast concrete beams are designed as under reinforced limit state. The bond performance of modified smooth bars are vital to avoid any debonding failure of the CFRPs in concrete, and the tensile strength of CFRP bars will be more optimally used if you can fail in tension. Although that is kind of a brittle failure, right? Materials and methods. So 2 stages. Stage 1 looked at pull-out testing to try to ascertain how much of an improvement the surface treatment would provide. And then stage 2 was larger full-scale testing of 9 precast inverted T-beams. And you can see the code of practice that was used to design or utilize the testing methods in stage 1 and stage 2 of this research program. Here you can see surface treatment and the cover. Let's take a moment to kind of look at this. The first number, C1, represents the specimen numbering. The second, you'll see an S or EC or DE. S stands for smooth, no surface treatment. EC in this specimen 2 and 3 represent epoxy coating treatment, and here it reports that the thickness is approximately 1 millimeter circumference around the bar. And DE is a treatment for deep embedment, which was set 4 and 5. And then AA is additional anchorage by using an aluminum tube. So that's literally bonding a tube to the section and embedding that in terms of the anchorage system. And then the location, the third designation, stands for centric position or eccentric position in terms of the testing. So I guess that would give you some edge cover or limit edge cover. And this you can see by the check marks, or which sort of was the smooth bar, the 1 millimeter coating, the deep embedment, the additional anchorage, and so forth. And in this picture you can see the process of the pull-out testing. So on the upper left, we see the smooth bars in the top, and then we see the coated bar with 1 millimeter thickness here in terms of these test specimens. And the next one shows the CFRP bar coated, again, 1 millimeter, and the additional anchorage at the ends, or near the ends, I guess I should say, of the specimen. Fabrication, curing, here's the deep embedment, and then the test setup for the pull-out testing. And it looks like they're trying to measure slip on the ends of these. Yeah, here's a closer detail of the test setup. And here you can see measuring at the ends of the member to determine how much slip relative to elongation in the bar location. So the Flexural test details, here you have a series of 3 beams, 4ST, that stands for 4 steel bar reinforced, so that's, let's call that series 1. And I won't go into the details of the geometry, that's listed there. Series 2 is 4 CFRP, so that has 4 CFRP bars as the longitudinal reinforcement, and then 6 CFRP bars. And I'm not exactly sure in terms of the reinforcement ratios relative to the 3 series. So that's probably in the paper, I would imagine. This is then the cross-section of the inverted T-beam. Here you can see the geometry in metric units. And you can see the longitudinal reinforcement. This one shows 10. Okay, here is the CFRP bars coated with the 1 millimeter thick, with the additional anchorage all kind of laid out, and the cages for the reinforcement of the inverted T-beams, the fabrication stages here. And here you can see the test setup in a 4-point loading configuration of the inverted T-beam. And it looks like they're measuring deflection, mid-span, and maybe quarter span. I'm not exactly sure. But 4-point loading test, and you can see some measurements both near the support. So the results and discussion. First in the pull-out test here, so remember we had smooth, we had the 1 millimeter thick, the larger anchorage, and then the larger block out. And if we take a look, we're dealing with an 8 millimeter diameter bar. It looks like there's some variation in the compressive strength, so that may need to be considered in terms of normalizing the pull-out capacities. But the failure mode in all cases was bar pull-out. But if we take a look at the smooth bar and the normalized bond strength, for the smooth was quite a bit lower. What is that? A magnitude of roughly 10 times the epoxy coated. And then the deep embedment had more than double the capacity of that with the 1 millimeter. And then the epoxy coated also had a little bit of an improvement there. So you can see that the average bond strengths, kind of the takeaway, achieved the minimum requirement in bond strength for these modified CFRP bars to be applied as flexural reinforcement based on the work that Brahim did in 2002. So let's look at the results of implementation in the beam specimens. Again, Group A was just the kind of the benchmark using steel. Group B had 4, and Group C had 6 CFRP tendons. Generally, you can see pretty similar first crack, which we would expect to be the same, really, when that first initial crack forms in the tension side of the concrete beam under the 4-point loading. If we start to look at the capacity of the steel, and again, I didn't necessarily see what the diameter of the steel was. Here we do have the reinforcement ratio, so 0.22 with the steel, 0.66 with 4, and 0.99 with the 6 CFRP. All of them displayed a tension-related failure, and you can see in terms of P ultimate that it looks like the Group C, there was issue with one of the tests here, but it seems like Group C gave greater capacity due to the higher tensile capacity prior to failure in the CFRP bars. Schematically, here you can see the observations of an increase in the CFRP ratio. So it enhanced the ultimate load 45 to 55% in terms, and the controlled deflection. The lower modulus of elasticity helped to reduce the ultimate load of the CFRP beams. And again, this sort of compares beam 1, beam 2, and beam 3. This reports the cracking moment and the flexural moment capacity. That was shown a little bit earlier. If we now look at what the ACI code would predict here in for the cracking moment, that looks like that would predict a higher cracking moment than was actually observed. And if you look at that ratio, it appears that the cracking moment is unconservative here. That's kind of odd. I don't know. Here you can see the crack patterns displayed in the left image. That's a pretty good, I'd say, crack distribution, and crack width looks pretty narrow to me. And here this shows the failure, typical tensile failure with several of the flexural cracks at pre-bending moment region. Again, in the pure bending region, which would be between the 2-point loads in the middle, here you can see the major tensile cracks develop and crack widths at that location. If we take a look now at the load versus deflection, and this is at midspan, the top one, let's see here. This one represents the steel. This one here represents with 6. And it's my understanding that these drops are when a major crack forms in the inverted T section for the 6th reinforced one. So there's a little bit of crack development at that location and loss in stiffness. So you can see in terms of load, a little bit higher in terms of load capacity at midspan. For beam series 2, again, similar behavior with the 4 and 6 tendons. If I go back one, you can get a feel for 250. You can see an improvement here with the treatment on the bars. And all of them together. And this shows the drop in terms of the inverted T with the 6 CFRP tendons and the formation and the drop in load associated with the 3 major flexural crack developments. So in terms of the neutral axis to depth ratio has been calculated here. And for the 4, it was a 0.19, and for the 6, a 0.28. Number of cracks, average crack spacing reported in this slide. And this is for the 4 tendon and for the 6 tendon. So, and finally, the strain in the concrete, in the, I assume, the compression zone, and in the tension zone and the reinforcement on the right. So you can see that a higher strain level is developed. Of course, the moment capacity is higher in the steel versus the CFRP. And the final conclusions. So prior to first crack, CFRP precast beams are stiffer than the steel. Cracking load, all beams have recorded nearly the same load. And then at cracking load, there was a sudden drop once that crack formed. And the crack numbers were easily identified from the figures. And that sudden drop has a negative effect in terms of beam stiffness, which increases the deflection and shifts the neutral axis into the compression zone, moving it up. Deflection, CFRP reinforced beam deflection, more than steel after cracking. And you can see the reinforcement ratio. The precast beam reinforced with 6, recorded lower deflections as compared to the beams with 4. And failure mode, no debonding failure in the CFRP bars and concrete. Hence, that surface modification provided sufficient bond and anchorage such that a smooth bar can be applied as flexural reinforcement. Higher concrete strength potentially could increase that first crack, of course. And thank you for viewing this presentation. I'll defer questions to the authors. Again, the paper is in the proceedings.